Welcome back to Quarantine Complex Analysis. Last time we proved a theorem that guarantees the existence of integrals. This is going to be a central theorem for us. We proved that if gamma has bounded variation and f is continuous, then the Riemann Stieltjes integral from a to b of f d gamma is, it will exist. That integral is defined in terms of a limit, and so we always have convergence issues, and this theorem will demonstrate that exists. We're going to need to do more work on the existence of integrals because we don't have a theory for making it easy to prove that a function gamma is bounded variation, but we'll get to that. First, though, we're going to talk about the Ml inequality today. The Ml inequality is a simple but surprisingly powerful inequality involving integrals. This is a picture, this is going to be an illustration of the Ml inequality in the real case. We're going to sort of talk about what it means in the real case, and then we're going to transfer it to the complex case. So let's imagine that we have a function f, and we want to calculate the integral of f from a to b. So that's graphed here in black. This will count as negative area. This will count as positive area. The Ml inequality for a function f simply compares its integral to the area of a rectangle, which is represented here in this pinkish color. So if we look at this entire rectangle here, then, well, that will be larger than the integral of f. So what could be simpler than that? So the statement of the Ml inequality in this case, if we have a function f defined on AB, will be if f in absolute value is less than or equal to m, then the integral from a to b of f of x dx, this is the ordinary real integral, not the Riemann Stieltjes integral. This integral will be less than or equal to m times L. And here, L is going to be, of course, b minus a. It's this length between. Now, this is such a simple inequality that you would expect that it's probably pretty easy to prove, and indeed it is pretty easy to prove. You might expect that it's not very useful because it's so simple, but in fact it's tremendously useful, and not so much because we want to bound integrals with rectangles. That's really not the point. The point is that we want to understand how integrals of some functions may be related to integrals of other functions. So an illustration of this situation is here. If we have a function f graphed in black and a function g graphed in red, and if they are pretty close to each other. So let's say, for example, that we can bound the difference between them. F minus g absolute value is bounded by m. Well, if we have, so m is this now rather small distance between those graphs, then we can conclude from the Ml inequality that the integral of f of x dx minus the integral of g of x dx, both, of course, from a to b, that will be, so take absolute value, that will be equal to the absolute value of the integral of f of x minus g of x dx. And this integrand here is now bounded by cap m, right? And so this is going to be less than or equal to m times b minus a by the Ml inequality. So this is where the Ml inequality really starts to shine. When we have two functions that are close to each other in an appropriate sense, then the integrals of those functions cannot be very far apart. They're bounded by this inequality. So that's the real value of the Ml inequality. Now, before we can start proving this, our situation that we want to work with is the general Riemann Stieltjes integral. And so we don't want to assume that these are functions on the real, from the reals to the reals. We want to assume that these are functions from the complexes to the complexes. And we also want to assume that we have some gamma floating around, and we're doing a Riemann Stieltjes integral d gamma. So our statement of the Ml inequality is going to look slightly different from what is suggested in these pictures. So let's state the Ml inequality. So this is our Riemann Stieltjes version of the Ml inequality. We have a function gamma with bounded variation, and the variation is bounded above by L. So in place of this b minus a being equal to L, we're using the variation of gamma, and we're assuming that that is less than or equal to L. Then we have another function f from AB to C. Notice I'm not assuming that it's continuous. It doesn't actually matter in this theorem whether it's continuous. So we have this function, and we know that we assume that the absolute value, well, the modulus of that function is bounded above by m on, that is for all x in the region AB. Then the integral of f d gamma is in modulus is going to be less than or equal to ml. Now notice here that the hypotheses here, the hypothesis on gamma bounded variation is what you might expect. You might expect a continuity assumption on the function f. Without that continuity assumption, we don't even know that this integral exists, but it might exist sort of accidentally for a discontinuous function. It might exist, and I don't want to over-restrain this theorem. So here, I'm simply going to say, provided the integral exists, right? So if the integral exists, then it will be less than or equal to ml. And if it doesn't exist, well, then there's no sensible inequality that could be stated for it. So this is going to be the form of our Ml inequality for Riemann Stieltjes integrals for complex valued functions. Now, the proof is very, very easy. The reason it's so easy is that the integral is a limit, right? It's the limit as partition norm approaches 0 of a sum, and that sum depending upon the partition. Now, so we don't need to analyze the limit in order to prove the Ml inequality, because every one of those integral estimates, every one of those sums inside the limit is already less than or equal to ml. So what we're going to do is we're just going to prove, we're going to claim here for any partition P of AB, the integral estimate, which is really the interior of that limit, the summation that is inside the limit, the integral estimate summation I equals 1 to m of f of tau I gamma of ti minus gamma of ti minus 1, that estimate is, well, the modulus of that is less than or equal to ml. And now my grammar is wrong. So the integral estimate satisfies this inequality that its modulus is less than or equal to ml. And if the modulus of every one of those is less than or equal to ml, then when you take the limit, then the limit can't exceed ml either. So that's what we're actually going to prove as we prove the Ml inequality. So it's nothing more than a simple triangle inequality on that sum. So you could probably work it out yourself, but let's do it together. So so the modulus of this summation, I equals 1 to m, f of tau I, gamma of ti minus gamma of ti minus 1. And modulus is, that's going to be less than or equal to, by the triangle inequality, the summation, I equals 1 to m, of modulus f of tau I, and then modulus, sorry, that's supposed to be in parentheses there, and then modulus gamma of ti minus gamma of ti minus 1. So I have applied the triangle inequality to distribute the modulus across the summation, and that's why I have a less than or equal to here. And I've also taken the modulus of each of these products and rewritten it as the product of their moduli. So I've distributed it across the product there as well. Now, these things are all non-negative, and these things are all bounded above by m by assumption. And so this is going to be less than or equal to the summation I equals 1 to m of m times this modulus ti minus modulus gamma ti minus gamma ti minus 1. I miswrote it. So gamma ti minus 1. And now that these have been, so those bounds are going the right direction because these terms are non-negative, right? If that were a negative term, then using the upper bound for m would reverse the inequality, but it's not, it's non-negative, so that's fine. Now that these have been bounded above by a uniform value m that doesn't depend on the summation index I, that m can be factored out. And so this is actually equal to m times the summation of the modulus gamma ti minus gamma ti minus 1. But that is equal to m times the variation, times the variation of gamma with respect to the partition P, which, because the variation is the supremum of these variations with respect to various partitions, is less than or equal to m times the variation of gamma, which is by definition, well, which is by assumption, less than or equal to m times L. So basically, the integral itself is the limit of these without moduli. And the modulus is continuous, so the limit, the modulus of the limit is equal to the limit of the moduli if they exist. And so basically having this bound for each of the terms inside that limit gives us the bound for the limit itself. So thus, if the limit exists, then it will be less than or equal to ML. So we get the integral from A to B, f d gamma has a modulus less than or equal to ML if it exists. And that's all there is to it. That's the proof of the ML inequality.